Hi everyone, welcome to Unit 3, Video 4. In this lesson, we're going to explore one of the most practical applications of calculus, work. Okay. I'm going to begin with some basic definitions and move to how you calculate when force is constant. Then we're going to learn how calculus helps us compute work when force varies with position. Along the way, we're going to explore some real-world examples like lifting objects, stretching springs, and things that deal with fluids. All right. I'm going to clarify some differences between the metric and U.S. customary system as well. So let's get started. So I'm not going to read all this, but work is basically a concept we hear in everyday life. We talk about work a lot in terms of jobs, right? A lot of colloquialisms, or how much effort it takes to do something. But in physics, work has a precise definition. It's the force applied to an object times the distance it moves in the direction of that force. So we have some examples, whether it may be pushing a box, whether it may be lifting a weight, or pulling a spring, right? These all require work. When force changes over distance, that's where the calculus comes in, right? So we want to think back to how we use integrals for area and volume, how we slice things into small parts, and then we estimated each of those parts and summed them up. We're going to do the same thing here. We're going to slice motion into tiny pieces, compute the force at each position, and multiply by a small distance, and then sum them up all using integrals. Now, we're going to look at how calculus helps us model the real world effort, motion, and energy in terms of work. Now, intuitively, you can think of force as describing push and pull of objects. For example, if you push a book across a table, or the downward pull of Earth's gravity on a ball. In general, if an object moves along a straight line with a position function, S of t, then the force F on the object in the same direction is given by Newton's second law of motion as the product of its mass and its acceleration. Force is equal to m times a. Now, in the simplest of terms, or the simplest case, is where the force is constant. If the force is constant, the formula is simple. Work equals force times distance, or W equals F times D, for short. Now, in the metric system, mass is measured in kilograms, displacement in meters, time in seconds, and force in newtons. Okay, we see that 1 Newton on a mass of 1 kilogram produces an acceleration of 1 meter per second squared. The fundamental unit that is used in the U.S. customary system is the pound. So in order to get a pound in the SI, or to get force in the SI system and the U.S. customary system, will be a little bit different. I'll show an example of that in just a moment. All right. In the case that acceleration is constant, so is the force. All right. Now, we also see that force, and this should be a big F here, we see that the force is measured in newtons and D in meters, right? The distance in meters, all right? And we call that unit of work a joule, right? So force times distance is joules in our metric system, right? F is measured in pounds in the US system, and distance is measured in feet, and we end up with our work being the foot-pound. The unit for our work is the foot-pound, so very important, which is 1.36 joules approximately. Now, let's look at an example of in the metric system, right? We have a 1 kilogram book that's lifted off the floor onto a desk that is 0.7 meters high. Well, before we can say work is equal to force times distance, we have to actually find the force, because right now we have it in terms of mass. And so because we assume that acceleration is constant, right? The gravity of on Earth, right? The force you exert is equal and opposite that. So instead of negative 9.8, we have positive 9.8. We have 1.2 times 9.8 equals 11.76 newtons. And we can take that and plug that in to our formula for work. So we have 11.76 times 0.7, and that gives us 8.2 joules of work, or energy. Now in our second example, where the force is constant, right? We already have our force in terms of pounds in this system. So we just have to multiply it times the distance, which is 6 feet off the ground. We have 120 foot-pounds as our work done. Two simple examples, all right? Now, in both these cases, right, the force is constant, so we can just multiply, which is very easy. But what if the force varies as the object moves? All right, for that we need integrals. We see what happens when the force varies. We have a different formula. So W is equal to the integral from A to B of f of x dx, right? And we assume f of x is continuous over the entirety of the range from A to B. Now, here's a short proof. We included this, right, just to give you a little bit of background. I'm going to leave this for your teachers to kind of go over and explain with you if you have more questions. Again, we're taking that concept of small slices and summing them up, all right? But the small slices that we're looking at is our distance and the work done over those small distances. Now, we want to look at an application where the distance varies, right? So it says when a particle is located at a distance of x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equals 1 to x equals 3? All right? So our work let me erase that. Our work, right? We see our work done formula here, and we're just going to substitute from x equals 1 to x equals 3. And we're just going to integrate this. We get 1/3 x to the third plus x squared from 1 to 3. And we evaluate that. When I evaluate that, just a quick substitution. I get a total of 50 over 3, approximately 16.67, right? And we don't have any units because we weren't given any units. So this can be your final answer, or you could have left it as 50 over 3